Hi everyone, how are you all? So today we are going to see some more questions on direct map cache, and then we will see a different type of cache which is called set associative cache. Okay, so let's get started. Let's see this question. Just to rephrase that or just to recall that what we have been doing. Let's see this question first. Can you try this question and can you tell me what is the answer you are getting? See, this question is saying that you have 64 kb. What does this k mean? Can anyone tell me? See, if you see k in computer organization or operating system, I mean wherever you see the k, that is dealing with the computer. Okay, not the computer networks. Which means that if it is not the network related thing, if it is just a computer thing, then k means what? 2 power 10. M, which means mega, it means 2 power 20. G, which means giga, it means 2 power 30, right? Okay. So these are the translations. Now, if someone says that 64 KB is the cache size, so cache size is given to you as 64 KB. 64 means 2 power 6, K means 2 power 10. These many bytes is given to you and has 16 byte block, which means block size is also given to you, right? What is the block size? 2 power 4 byte. If addresses are 32-bit, okay, so which means if let's suppose you have 32-bit address line, okay, total address is 32-bit. How many bits are used for tag, index, and offset? So do you recall this? Offset means if it is 2 power 4, then 4 bits for offset, right? 4 bits for offset. What about the middle one, which is basically once you remove the offset, then what you get? What is this? What we can call? Can anyone tell me? Can anyone tell me this particular thing? We call it block number, right? If you recall, then we can call it block number also. So we say that, okay, once the offset is removed, then whatever is remaining with us is actually the block number, right? So this whole thing is a block number. Now what you can do, you can further divide, right? You can further divide this block number into two parts, which is what we call it. We call it index and tag. So this is basically the line number or the index. So if you see that how many lines should be there, see the cache size is given to you. Okay, the block size is given to you. It means the number of lines you can find out, right? How many lines are there? I think there are 2 power 16 divided by 2 power 4, which means 2 power 12 lines are there. It means 12 bits we need for the line number, right? Or we also call it index. For the index, we need 12 bits. For the block offset, some people call it byte offset also, but let's just call it offset. For offset, we need 4 bits. The remaining one is something called as tag. For that, how many bits we need? This is 16. So 16 bits we need for tag. Is this fine to everyone? Let me know. Easy question, but still let me know. Okay, understood. Cool. So now what is this? This tag? Tag will be 16. Okay, I hope you understood. So how we are calculating? This is index. We are calculating based on how many lines we have, because this will tell you the line number. This is the line number, right? The whole thing is a block number. Okay, the whole thing, whole of this is a block number. Okay. Now let's just see this question. A computer system uses 16-bit memory address. So here, how many bit you use? 16-bit. It means what? It means if you are using 16 bits, then what should be the memory size? Can anyone tell me in terms of bytes? If memory is byte addressable, okay, don't worry if it is not given, but memory is byte addressable unless until it is given. So it means 2 power 16 bytes, right? With 16 bits, you can represent 2 power 16 bytes. Okay. So, I mean, you can represent 2 power 16 different numbers. And if each of this address, I'm saying it is a byte address because memory is byte addressable. So if each of this address is a byte address, so this means we have these many bytes, isn't it? So 16-bit means these many bytes, right? Or vice versa. These many bytes means 16-bit. Okay. Hope you already know these things, right? Okay. Now, what it is saying, it has 2 KB cache. So the cache size is given to you is 2 power 11 bytes, direct map manner, with 64 bytes per block. Okay, so block size is given to you is 2 power 6 bytes. Can you tell me number of blocks, number of lines, or number of blocks here? It will be 2 power 5, right? 2 power 5, which means the block offset, you can definitely tell me 6. Here you can tell me 5. So remaining is, this is 11 and remaining will be 5, right? So 556 should be your answer, right? That question I have taken from this university. Let's just see. Offset is 6, and then the 5, right? The remaining one is 5. Okay. Easy one, right? Understood? So this was just to recall you that what we have been doing. So we can definitely find out tag, index, and offset. Let me just recall you that what we have been doing. So basically, we said we have, let's suppose, some memory here. Okay. These are some blocks, right? Now, if you want to map, let's suppose these are the four lines we have. If you want to map this particular block, then it should be belonging to, let's suppose this is line number 0, this is line number 1, this is line number 2. Okay, I mean, I can write in decimal or I can write in binary. This is line number 0, this is line number 1, this is line number 2, this is line number 3. Can anyone tell me technically what we call it? Do we call it tag? Do we call it index? Do we call it offset? Line number, we call it what? There is a technical name for that. What we call it? Can anyone tell me? Yes, this is called index actually. Okay. Anyway, this is implicit, right? I mean, this is 0, 1, 2, 3. There is, I mean, should we be storing this? Should we store this index explicitly? Do you think? No, right? It's very implicit. Have you seen operating system lectures? In page table, we do not store the page numbers, right? See, this is for page number 0, the page number 1, page number 2, page number 3. If you have seen the operating system lectures, then it is related to the page table also. Okay, anyway, this index are implicit, but that's fine. So what we have been doing in direct map cache, we were saying that this is the block, first block 0, or the first block. Okay, so this is the first block. This is mapping to which line? Can anyone tell me the number here? This is mapping to 0. Then it alternatively like keep on repeating, right? 0, 1, 2, 3, then 0, 1, 2, 3, right? Do you recall this? This is 0, 1, 2, 3, 0, 1, 2, 3. Or do we say that these two are mapping to 0? No, right? This is 0, 1, 2, 3, 0, 1, 2, 3. It will keep on repeating, isn't it? Okay. I hope that is fine to everyone. Now, what I'm saying here, that whatever is your memory address, okay, let's suppose this is of 16 bits or whatever, right? Doesn't matter. So whatever is your memory address, first you do what? You find out the block number, right? So here, if there are, let's suppose 8 blocks, so it will be how many bits? Your block number will be 3 bits, right? 3 bits. Is this okay to everyone? See, how many blocks are here? Let's suppose there are 8 blocks. Then the block number, this is the block number. Now, if I further ask you that this particular, any of the block is belonging to which particular, let's suppose line, then you can further divide it. Then you can tell me the line number also. Okay, line number. Let's just do more question and then you will get to understand more, right? Let's see this question, what they are saying. Given a 12-bit address, which is JKLMNOPQRSTU. Okay, so here J could be either 0 or it could be 1. Okay, I mean, this is some address in binary, but they are not telling whether it is 0 or 1. I mean, just make it, just keep it abstract, which means let's just take it JKLMN or JKLMNOPQRSTU. Okay, where J is the highest order bit and so on, right? Now they're saying the direct map cache is used with 32 lines. So number of lines is given to me. Can you immediately tell me how many bits you will be needing for index? If someone asks you the index, how many bits you will be needing for the index? Can you immediately tell me just because of the number of lines are given to you? Everyone, just tell me it should be 5 bits, right? Okay, that's fine. Now they are saying 8 byte blocks. With this information, can you also tell me immediately that what are the basically number of bits? How many bits we will be needing? So here I will be needing 5, right? Here I will be needing 5, and for the offset I will be needing 3, right? Okay. If it is 12, then the remaining one. See, this is the index. For index I need 5. Here I need 3. This is index. This is You can say it is offset. And for the tag, how many bit I need? If this is tag, then you have 8 and remaining is 4, right? So for tag, you need 4 bits. That's fine. Now they're also saying that answer by putting one or more letters in the box. K, L, M, N would be second, third, and fourth bit, which means they do not just want the number of bits, they also want which bit. So can you tell me that if this is 3, then which bit are 3? STU or JKL? What should I write here? Here, STU or JKL? The least significant or the most significant? The least significant, right? So STU you should be writing here, and then next 5 bits, which means I think NOPQR. NOPQR you can, sorry, next 5, yeah. NOPQR you can write here. And the remaining JKLM you can write here, right? So that's how you can solve this question. Easy question which I have taken from this university, right? So NOPQR, JKLM, right? And STU. Okay. Understood this question? Okay, let's just see more questions because there are many questions that we want to solve. Okay, this question is basically very nice question. It will hit directly to the basics. Okay, if you can solve this question, I will be very happy. Can you try this question? What they're saying, let me just read out this question. They are saying that cache size is given to you, which is having 64 blocks or 64 lines, right? Okay, and block size, each of the block is having 16 bytes. Then this byte number, if someone tell you byte number 1200 byte, this is the byte number. It is mapping to what line number does this byte address map to? So can you tell me this is the byte number, right? Byte number or the address, it maps to which line? Line number. Can you solve this question? We can solve this question by converting this 1200 into binary. Okay, then I can see that, okay, what is the line number? So you can definitely do it. Can anyone google out binary for 1200? Meanwhile, we can do with the binary, but I want you to do with the decimal. Can you do with the decimal? See, what we first have to divide. If you recall, then what we are saying, let's just first find out the block number, isn't it? Shouldn't we finding out the block number using the line number? So you just tell me what should be the block number here first. Okay, before you tell me the line number, you tell me the block number. How do we find out the block number? What we will be doing? Take this byte address. This byte will be in which block? If each block is having 16 bytes, then this byte is in which block? See, you tell me the byte number. Okay, you tell me the byte number, which is, let's suppose, 1. Okay, you tell me the byte number 1. It is in which block? The block 0. Byte number 0 is in block 0, right? 0 to 15 is in block 0 only, right? Then 16 is in block 1. 17 is in block 1. 18 is in block 1, isn't it? So these are the byte numbers. If each block is having 16 bytes, so isn't it the case? Right? So similarly, 1200 divided by 16. Should you be taking floor or seal? See, if 17 you need to find out, then what you did? This is belonging to byte number, the block number 1. Then what you did? You have taken floor or seal here. You have taken floor, right? So similarly, you can divide and you can take the floor, isn't it? Now you tell me what is the answer? 75. If you do this, then 75 is the answer, as Yamini is saying, right? So like she has given the answer way before I explained. So that's really nice. So she's saying that 75 is the block number here. Understood? Okay. Now, once you find out the block number, now you tell me if this is the block number. Now you tell me the line number. Now what you will do further? You will see how many lines are there, right? So they are saying 64 blocks. So which means 64 lines are there. So what you will do? See, if I tell you the block 0 is mapping to line 0, block 1, line 1, and so on, right? So block, let's suppose 63 is mapping to, sorry, yeah, block 63 is mapping to line 63. This is the block number. This is line number. Okay. And then then block 64 is mapping to again 0, right? Again line 0. So what you're doing, if given the block number, I ask you to find out the line number, then what you're doing? You're just taking the remainder, right? So 75 is the block number mod number of lines here. This will tell you how much it is. This is 1, right? Okay. So 75 is the block number, and they are saying 64 blocks we have. Yeah. If they have 64 blocks, that map case with the 64 blocks. So it is you can say line number. Sorry. We are finding the remainder. Not the divisor. So how much the remainder will be? 11, right? This is the remainder because this is a mod operation. So that's why it is a line number. Understood? Let me just explain you again. Okay. Let me just explain you again. So first of all, you tell me for the same question, let's just explain with the binary. Okay, then I will again come to the decimal because I want to hit the basics, right? No, I don't want you to just I mean by heart the things. Just see that how the things are getting driven from the first principle. For that, let's just see using the binary. Can you tell me what is the binary of 1200? You can just Google out and you can quickly tell me. Okay, so this is just use the space. Okay, so use the space after 4 bits, but anyway, that's fine. So this is 1001, I think, and then this is 0110, and then 000, right? Okay, so this is the binary for 1200. Okay, if I have written correctly, 4 zeros, 110. Okay, now you tell me that if block size is 16 bytes, then what is the block offset? 2 power 4, right? This is the block offset. Can you tell me? Can you tell me the block number? Can anyone tell me the decimal representation of this if you want? If you calculate the decimal representation, it's very easy. 2 power 0. This is 3, right? This is 9, and okay. So if you calculate, this is coming out to be 75, right? This will come out to be 75. Okay, which is a block number, right? But anyway, that's fine. So this is the basically block number. But they have not asked you the block number. They have asked you the line number. So what you further need to do? How many blocks are there or how many lines are there in the cache? 64, which means 2 power 6. It means what? If you do 2 power 6, then you take 6 bits here, right? So 1, 2, 3, 4, 5, 6. These are the 6 bits. So if you just take these 6 bits, then what it will tell you? What is the answer? So this is going to be the line number. That's what they're asking, right? So can you tell me what is the line number here? This is nothing but 11, right? This is the line number, which is 11. Okay. The block number was 75. So that's what you can do in binary. That's fine. But can you also do in the decimal? That was the question. Okay. Without converting into binary, because this number could be very big. Okay. This number could be very big, and then you might not need to do it using the binary. Maybe you can just use the calculator, which is very much comfortable in the decimal, right? So you can use your calculator and find out this answer. So how to do it? Let's just see using the decimal. Is this binary okay to everyone? Should be okay, because that kind of question we have done many times. Okay, so this particular thing should be okay. Now let's just do the same question using the decimal, because my intention to put this question is to see that if you are comfortable in the decimal also. Okay, see, they are saying there is a byte which is 1200 byte. Now you tell me, let's suppose this is the memory. Okay, let's suppose these are the 0th byte to 15 byte. Okay, these are the next 31. These are the next 15 bytes. Sorry, next 16 bytes, and so on. Okay, if someone asks you where does this, in which block, this is a block 0, this is a block 1, and so on, right? Where does this byte number, somewhere this byte 1200 reside, right? Where does this byte number 1200 reside? If someone asks you where does this byte number 0 reside, what you did? Or someone asks you where does this byte number 16 reside, you can just take divide, right? Where does this 17 reside? You can see that how many times you can divide. Where does this 18 reside? You're dividing one time, right? You're dividing one time. So where does this 1200 reside? In which block? They're just asking which block. Can you tell me the block number? Where does this 1200 reside? You can just divide and can take the floor, right? Because from these examples you can see that okay, 8 for 18, divide and take the floor. For 19 we are saying 1, for 20 we are saying 1. So you can divide and take the floor, right? So these are the different blocks. So this must be the block number how much? 75, right? This must be the block number 75. Very easy. Should be okay to everyone. Which means this 1200 divide by what is the block size? I think 16. Then this is 75, right? 75 point something, but doesn't matter because we are taking the floor, right? This is the block number. Now, once you have the block number, what you are doing? Once you have the block number, you want to know that this belongs to which particular line. This is from line number 0, this is line number 1, and so on. So if you want to get the line number from the block number, that's very easy. How you do it? We have been doing it. We are doing the mod, right? We are doing the mod. So mod 64, which means the remainder will be 11. So ultimately what you are actually doing is something like this. Let me just show you side by side how we are doing in the binary and how you are doing in the decimal. See, you have some 1200, which is some address, right, in binary. Now first you do what? You find out the block number, which means to find out the block number, you say that okay, this is your block number, right? Then if you're talking about this part, see, you have block size of 16 bits, 16 bytes, right? Which means here you are saying it is 4. Now if you're talking about this part, then you are talking about the mod, or you are talking about the division, remainder, or the like division means you understood, right? I mean this the real division. Okay, so see, if you are talking about this part, then this is the mod. If you're talking about this part, then this is the real division, right? This division. Now once you take this, then you are interested in this part. Then you tell me this is a mod or this is a division. Once you get the 75, now you are interested in this part. This is basically a mod, right? This is basically a mod. So that's how this binary and this decimal goes all together. In binary, I agree, things are very easy, okay? But you should know that how things are happening with the first principle, because you never know that in Go classes test series you will see this, right? You will see some question from very first principle. Let me tell you one instance that I think yeah, in AIMT 1 there is one test that we have taken, All India Mock Test 1. I have put the similar kind of question in operating system. Okay, I was just asking the simple conversion, and just that I have given the number in decimal. Okay, there were rarely people were able to do it, and I was very surprised. And to be honest, before even putting that question, I was thinking that I should not put that much easy question, because this is just a division. I should not put. But then I thought that okay, let's just put it for 1 mark. Later I found out that even the toppers were not able to attempt it, because they got confused that what to do with that. Okay, so you should know the things with the first principle also. Is this fine that what we are doing here? Okay, once the idea is clear that okay, block number, and from block number you want the line number, then you can definitely do using this also, right? So first division, then mod. Isn't it a good question? Tell me. It's a good question, right? Okay, now let's just see more questions. So today we will see some more good questions. So this is the answer here. Now you have noticed one thing, that in direct math what we are doing, we are saying that okay, maybe this block number 1, right? Maybe this block number 1, or this block number 5, or the block number 9, or the block number 13, all of are mapping to this particular line, right? But how to determine that which block is currently in slot 1? Which means let's suppose this is X, this is maybe suppose W, this is let's suppose Z, this is let's suppose Y. Okay, now let's suppose CPU has generated some address. CPU want the byte from this particular block, let's suppose, okay, the block number 1. Now it will check For the block number one, it will check this particular line, whether this line is empty or this line is filled. That we tell using some bit called valid. Okay, if this valid is one, it means it is valid. Otherwise, it is invalid. If valid is zero, CPU can check whether it is empty or it is filled. Okay, valid or invalid, basically. Okay, we will talk about it later on. But for now, understand that what I'm saying, that let's suppose that CPU says that okay, I want something from block number, let's suppose one, or maybe block number five. Currently, let's suppose X is there. Currently, let's suppose X is there. CPU will check, okay, I want something from block number five, right? CPU wants something from block number five. CPU wants, let's suppose, block five. What CPU will do? CPU will check whether the step one it will do whether this particular field, this particular the line is empty or filled. Tell me it is empty or filled. This particular line is filled, right? Since this particular line is filled, now what CPU will do? CPU will say that okay, this particular line is filled, which means valid is one. That's great. Okay, I mean we will talk about the valid and invalid later on, but let's suppose this valid is one. CPU will say that okay, this is filled. Let me just fetch this. Is this the correct block CPU wanted? Ultimately, CPU wanted what? CPU wanted Z, right? Because CPU wanted this block 5. So CPU wanted Z. So my question is that how CPU will get to know that it has X or Z? Getting my point? So CPU want the block 5. It will do what? It will go to the cache line 1. It will say, okay, this is filled. Let me just fetch it. Isn't it? So how CPU will get to know that this is containing the block 5 or block 9 or block 13 or block 1? Shouldn't be also knowing that this is containing which particular block at this point in time? Because this particular slot or this particular line can contain either 1 or 5 or 9 or 13. Shouldn't we know that this is currently containing which one? Is this really needed or not? Tell me. This is needed, right? So we want to know, right? Since the cache can contain any of this. Are you getting my point, what I'm trying to make? So the cache can really contain okay, or maybe cache, you just say cache line 1 can contain any of the block, right? From 1, 5, 9, 12. So we should know at this point in time what it is containing, at any point in time what it is really containing, isn't it? So we should know containing at any given point in time. Understood? So have you understood the problem? See here that these many of the block can map to, let's suppose one of the line. Let's suppose this particular line, right? So here this can map and this can map. Okay. So I'm currently, let's suppose I'm talking about this one and this one. Both of them can map to this particular slot, right? But it is currently containing, let's suppose this is Z, this is W. It is containing Z or it is containing W. We should know this, right? So how we will be knowing this? There is a bit called tag, so using which we can know this. See what is happening here. What we did, let me just tell you. We had the actual byte address, right? This is, let's suppose, 16-bit. Okay, let's suppose that our block offset is 4-bit, is our block offset. Let's suppose I have additional maybe let's suppose 6 bits for the line. Okay, line number. Now how many tag we have? We have 6 bits of tag, isn't it? For the remaining, sorry, 6 and for 10, yeah, 6 bits, right? So we have 6 bits of tag, isn't it? Now we said that okay, this particular block, this is the whole block, right? So we have divided the block number itself into 2 parts. Okay, this is the block number. We said this block number is of line number and the tag bits. So since it is of two parts, what I'm saying, that this block is mapping to some line number. Now this is basically unused till now. So this tag is basically helpful to let me know that particularly this line is containing this block or another block, which means see here, see what is happening here, that let's suppose that I say this block number 1. Okay, block number, this is 0 1, and what is this, this is 5, right? This is I think 9, this is 9 10 11 12 13, right? This should be 13. Okay. So let's suppose this block number 1 is mapping to the line number 1, and 5 is also mapping, 9 is also mapping, 13 is also mapping. Why they are mapping? Because this is 0 1, this is 0 1, the line numbers are 0 1 0 1 0 1, right? I mean, I'm just writing the block number. Don't get confused that how I'm using least significant bits to the line number. This is not least significant bit. I mean, I'm not writing currently here the byte offset. These are the block numbers I'm writing. Okay, so I'm basically talking about this middle bits. This is 0 1 0 1 0 1. So since each of this is sharing the same middle bits, so that's why each of this block is going to the same line. But now we should be knowing. Let's suppose this is X, right? Okay, X is there. Let's suppose this is W, this is Z. Okay, this is, let's suppose, Y. Now we should be knowing this is currently containing X, or maybe W, or maybe Z, or maybe Y. How we will say this? Using the tag bits. See, this block number, for the block number, these if these bits are same, that's okay. But these bits must be different, right? See, let's consider two block number. Let's suppose any of these two block number. If I say these bits are same, right, which means line number is same, should they be different or should they be same? I mean, can they be same also for two different block? Can they also be same? No, right? If they are also same, then binary pattern itself will be same. They have to be different. Kuch to different hoga na. There is at least one bit different, right? If they are exactly same, if these two are exactly same, then at least something is different. Some one bit is different at least, right? Somewhere. I am saying that for these two block number, these two are exactly same. Then this should be different, right? If these are the two different block numbers. So basically, what will I do? I am saying this is tag. I will maintain something called as tag. Okay. Now suppose currently it is containing X. Currently it is containing X. Can you tell me the tag number? What should be the tag? It should be 10, right? It should be 10. Why? Because I will say this is my tag, and now I will differentiate using the tag. So for example, let's suppose this is Y, and currently it is containing Y. What should be the tag? It is 0 0, right? It is 0 0. Understood? So what CPU will do now, if I maintain the tag, then there is also a valid bit, okay, which I'm not currently showing, but yeah, valid means this is valid or invalid. Okay, if I say, let's suppose this is maybe 1 0, anything, okay, 0. So this is 1. Okay, suppose if I say that this is 1, basically I'm currently interested in this one, then what is the first step CPU will do? CPU will check, okay, this is valid, great, right? So CPU has generated some address, which is tag, which it will divide into tag, block offset, or the index, right? Three things. CPU will do what as a first step? Can anyone tell me? As a very first step, what CPU will do? It will say that, okay, what is the index? What is the line number? It will go to that particular line, right? So using this index, it will go to that particular line. That, okay, I'm interested in this particular line. Should I explicitly store this index? Should I just like tag and valid bit? Should I explicitly store this index? No, right? It is very implicit. Like it is increasing order 0 1 2 3. So I can directly go to that particular. Let's suppose this is, let's suppose 0 1, right? So where will I go? If it is 0 1, I will go to the first line, right? I mean, I do not need to store this. I will go to the index, right? This particular one. Okay. Now, what is the next step CPU will do? CPU will check, oh, this is valid, great. Then what it will do? It will check whether these two are same, which means this tag, I'm interested in this tag. Is this also containing the same data? If it is containing the same data, then only pick it. If let's suppose I'm interested in 0, 1. It is containing 0, 0. Will I pick it? Suppose this is 1, 0, right? I mean, I said that, okay, I have generated the address, CPU generated the address for the some byte in this particular block. Maybe it could be anything, doesn't matter. So let's suppose CPU generated this address. If CPU generated this address, then this is hit or miss in cache. Can you tell me? Hit or miss means, have you found it or have you not found it? Okay. Hit means if you CPU will find it or not. So if CPU generated this address, it will go to that index. It will check, okay, in this index. Okay. Okay. So also assume that this is 1, 0. Okay. There is some data here. So will CPU say that, okay, this 1, 0 and this 1, 0 is matching? No, right? CPU will go to that index first, right? It will say that, okay, let me go to that index. And then is this tag, it is currently containing my data or something else, right? Because it can contain multiple possibilities, right? That we talked about x, y, z, w. It can contain multiple possibilities. So that's why CPU will see that, okay, currently it is containing my data or someone else's data. So basically, it can contain maybe x, maybe w, maybe z, maybe y. Now, if it is, let's suppose 0, 0, this tag is 0, 0. It means currently it is containing y, okay, and currently it's containing y. If it is, let's suppose 1, 0, then x. If it is 0, 1, then something else, right? So it will match this tag. If this tag is matching, then hit, otherwise miss. Let's do questions. After that, you will get to understand more. Okay, let's do questions. Okay, this is just something that I wanted to share. Let's do questions. Using the questions, you will get to understand. But have you little bit understood that what is the meaning of the tag? We need tag, right? We need tag bits. Okay, cool. Let's just understand. Let's just see the questions. Let's just see this question. So they are saying, consider the cache given which is filled with the some data. Okay, so this cache is filled with some data. Tag is given to you, right? Let there be 15 blocks in main memory. Sorry, there are 16. Okay, so I typed it wrongly. Okay, so let there be 16 blocks in main memory. What is the block number which reside in line number 0? What is the block number which reside? In other words, where did W come from? Can you tell me the block number? It is containing the data of which block? See, this is the line number 0. This can contain the data of 0, data of, if these are the 4 lines, then 4, data of, so for which it can contain 8 and 12, right? It will be containing data of either 0th block or 4th block or 8th block or 12th block. That's what they are saying. Now they are saying, if tag is 0, 1, then currently it is containing data of which block? It is containing data of which block? See, if you recall, this is tag, this is index, this is block, byte offset or block offset. So let's just only worry about the block number, right? So the tag is given to you, it is 0, 1. The index you implicitly know, right? Implicitly you know that this is 0, 0. Now can you tell me the block number? This is 4, isn't it? This is 4. So this is coming from which one? This is coming from 4, right? Block number 4. Understood? Let me know if there is any doubt. See, the tag is given to you, and then they're just asking that if this tag is given to you, then what is the block number which is having, I mean, which is currently in this particular line? Okay, maybe we can do more question, and then you can understand it more. Can you tell me here that what is the block number? X is coming from, where did X come from? Which block? So tag is 1, 1, right? Tag is 1, 1, and the line number is 0, 1. It means what? This is the block number, isn't it? So what it is? This is 13, right? This is 13. Okay, understood. Now let's just solve more questions. Probably you will get to understand. Can you tell me here, this y is coming from which one? So you know the tag. Index, 0001, 0001, and then 10, right? This is index which is implicit. No one has to tell you. So this is the block number finally. It means 2. Can you tell me this can contain data from which block if there are 0 to 15 or total 16 blocks? If it is line number 2, then maybe 2, then 2 plus 4, right? Which means 6, then 6 plus 4, 10, 10 plus 4, 14, okay? 2, 6, 10, 14. It can contain data from either 2 or 6 or 10 or 14. Currently, it has data from which block? Based on the tag, you can tell me. Currently, it has the data from which block? Block number 2. Okay, cool. Similarly here, uh, it can contain data from which blocks? Block number 1 plus 4. You do plus 4 because it is repeating with 4, which means 5 plus 4, 9 plus 4, 13, right? It can contain data from 1, 5, 9, 13, but currently it is containing from 13. How you told me? Using the tag, right? That's why tag is very, very important. Okay. Now you tell me here. This is the last question of this type. You just tell me here. Tag is 01. Index is what? Index is 11. So that's why it is 7, right? Nice. So it can contain data from, this is 0, 1, 2, 3, right? So it can contain data from block 3, and then plus 4, 7, then plus 4, 11, then plus 4, 15, right? 3, 7, 11, 15. Okay. So see, this particular W was coming from, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. 0 to 15. W was coming from 0, 1, 2, 3, 4, right? W was coming from 4 and so on, right? This X was coming from here, I think. And okay, this is Y, and I think this I can write it as Z. Okay, doesn't matter. So I hope you understood that what I'm trying to say, right? Using the tag, you can tell me currently it contains the data from which block. That's why tag is also very, very important. Okay, cool. Now, should I ask you one interesting question? Or maybe I can ask you after this, or maybe I don't know. Okay, let me just ask you one interesting question. Are you ready to answer this? This is going to be a bit challenging. Okay, just very intuitive but challenging. Suppose I say, here, how many bits I use for tag? 2 bits, right? 2 bits I'm using for tag. It means what? Does it tell you something? Does it reveal you something? That number of bits in the tag field. Does it reveal you something? It means that this particular tag can be, any of this tag can be from 00, 01, 10, and 11. So it tells me that or this particular line can contain data from how many blocks? 4 blocks, right? If it is 00, then some block number, maybe I can append 00, right? This is index, I can append, right? See, if it is containing, this particular tag is basically 00, right? Let me go to the next page probably. Let me just explain you that what I'm trying to say. See, if this could be anything, right? If it is 00, you tell me what is the block number it currently contains. If it is 00, then you will say the block number 0. If it is 01, then the block number, can you tell me? If it is 01, the tag is 01, then the block number 4, isn't it? If the tag is 01, then there will be the block number 4 because index is 00, right? If tag is 10, then the block number, then what is the block number? 8. If tag is 11, then what is the block number? 12, right? So basically, depending on the tag, you're telling me what are the block numbers. If tag is 2 bits, it means what? It means you can have 4 variations. I mean, there are 0001, 1011. It means what? It means that 4 block can basically 4 blocks are mapping here, isn't it? Does this number of tag bits reveal you something? Let me know. You understood this or not? that if the number of tag bits are 2, it means that there are 4 blocks which are mapping to this line. Okay, so let's just do question, and after that it will be more clear. Okay, so let's see this question. What they're saying, this is very interesting question. A computer system uses 16-bit memory address. It has 8 KB cache organized in direct map manner. So they are saying that 16-bit is the memory address. The total is 16. And 8 KB cache they have given. So cache size is given to be 2 power 3 into 2 power 10, which is 2 power 13, right? 2 power 13 bytes. Now they're asking number of bits in tag field. Can you solve this question? Number of bits in tag field. Have they given the block size? No, right? In this question, they have not given the block size. Isn't it? See, if the block size is given to be, let's suppose block size, if let's suppose I assume the block size is 2 power p. Okay. Then you can say it is p. And then how many lines will be there? Number of lines. 2 power 13 upon 2 power p. 13 minus p, right? 2 power 13 minus p. So this will be 13 minus p. What is the remaining one? I think 3, right? Which is tag. And that's what they're asking, isn't it? Understood what I'm saying? So if you assume the block size to be something, let's suppose 2 power p, then you can definitely solve this question. But I don't want to do this procedure. Can you tell me directly? Okay, with this, without assuming some block size, can you tell me directly how to solve this question? See, they have given you main memory size or the number of bits, which is 2 power 16, 16 bits, or they have given you the main memory size, which is let's suppose 2 power 16 bytes. They have given the main memory size. They have given you the cache size, which is 2 power 13 bytes. Okay, with these two sides, can you directly tell me the tag? Tag is nothing but ratio between these two. It is 2 power 3, right? It means tag must be 3 bits. Let me explain you how. See, let's suppose I have 16 bits, okay? What do we say here? That this is the block offset, right? Or let me just write offset. This is the offset. This is line number, right? This is line number. This is offset. Now, do these two things reveal you something? Suppose I say that so suppose I say, let's suppose that this is the offset. And then what is the remaining one? What is the remaining one? Block number. If that is the case, if this is a block number, this is a block offset, right? If that is the case, then the whole thing is called main memory size, isn't it? This is the whole main memory size. Let me know if this particular thing is clear to everyone. See, the given main memory size, we say that, okay, this is the block offset block number, isn't it? Is this okay? Or there is any confusion here? Let me know. See, if you are given the main memory size, then you will say that, okay, this is the block offset or the the byte offset, and this is the block number, right? Now, I further said that, okay, from the block number, you are finding the line number, and this is tag. Okay. The whole is main memory size, I agree. But just with this pattern, block number, block offset, line number, this is also line offset, right? I mean, because the size is same. Can you not say this is the cache size? This is the cache size? Tell me. So if this block number, block offset, or the or just offset, basically they are combinedly, we are saying this is main memory size. Why? Because whatever is the block number, and then you are basically also having the block offset, then you can tell me the main memory size. Similarly, given the line number, I also tell you number of bits in the offset or something, the line offset, because line offset and block offset is same, right? Given the line number, given the line offset, I can also say this is a cache size, right? So if this whole thing is main memory size, this is the cache size. Someone asks you to the tag. Can't you find out the tag? Suppose someone says main memory size is 16 bit. I mean, I'm just telling you in terms of bits. This is 13 bit. Can you immediately tell me the tag? This is 3 bits, isn't it? So from here, if someone is saying this is 16, this is 13, then isn't it directly 3? Or you have to do all of this calculation? See, the ratio is important here. The main memory and the cache are related with the tag, the sizes. Okay. This 3 bit is telling you, if this 3 bit means 2 power 3, right? Which means this 3 bit tell you what? That 8, that main memory is 8 times bigger than the cache, isn't it? Because 8 of the block are mapping to the one of the line. See, this 3 bits is telling you that main memory is 8 times bigger than the cache. Okay. See, this offset and this offset is same, which means you can call it line offset or block offset. Why? Because ultimately the whole block is going to one of the line, right? This whole thing, if something is useful here, that how much to go inside, offset means how much to go inside, right? In this, which byte number you're talking about, the same thing is here, right? It's just a place. You are keeping it, let's suppose, in the you're keeping it in Jaipur, or you're keeping it some data in, let's suppose, in Bangalore. Doesn't matter, right? How much to go inside will not change if I'm moving the whole thing, right? So the line offset and the block offset is same. Offset means which byte number within the block you're talking about, right? So let me know if this is making sense. So here what I'm saying, that see, if I say that, let's suppose the tag bits are 3, or maybe let's suppose I say it is 5 bits. 5 bits are tag bits. What does this mean? If this is the cache, it means that each of the line can contain how many blocks? How many blocks will be mapping to this line? Can anyone tell me? 32, right? 32. Why? Because each of this, if this is 5, each of this will uniquely tag me. See, this is the index is, let's suppose, whatever, 1, 2, 3, 4. Okay, let's keep it 4, or maybe let's say it is 8. Okay, I mean the index is, let's suppose, 3 bits. Doesn't matter. Okay, suppose index is 3 bits, which means this is 0, 0, 0, 0, 0, 1. Okay, and so on. This is 1, 1, 1. Now you tell me if this particular tag is containing 0, 1, 0, 1, 0, then can you tell me what is the block number in binary only? You can tell me the what is the block number that this particular currently this particular line hold? What is the block number? Currently this particular line hold. What is the block number? It is the tag 0, 1, 0, 1, 0 and the index, which is 3 zeros, right? This is the block number which currently this line hold, isn't it? If I, let's suppose, change this, anything, if I change this to 1, then the block number will change. So how many block number this line can hold at different times? 32, isn't it? So basically, this tag field is telling you that how much large in terms of multiple. Okay, how multiple of my cache memory, how much multiple is your main memory of your cache memory, which means if if tag bits are, let's suppose, 6, then what you can say, Okay, let me ask you whether which of the following is true. Okay, then main memory is six times bigger than cache memory. Okay, this is first option. Let's suppose as a second option I say, which is true. Which is true. Yes, C is true, right? C is true. C is true. So tag bits are telling you that each line is basically can hold. Basically, if you keep on changing, then the block number will keep on changing, isn't it? If you keep on changing the tag, then the block number will keep on changing. If this is 6, then there are 2 power 6 blocks that are mapping to one of the line, isn't it? So basically, if someone give you, let's suppose cache size to be, let's suppose 2 power 10 bytes, man memory size, let's suppose 2 power 16 bytes, and someone asks you what is the tag field, then can you tell me number of bits in tag? 6 bits, right? Okay. See, this is the main memory, which is 16 bits. And cache size, basically this whole thing is also cache size apart from tag, okay, which is given to be as 10, right? So this is 10, combinedly this is 10, so remaining is 6. And now next someone asks you what is the index, then what is your answer? With this data, can you determine the index? No, right? We cannot find with given data. But can you determine the tag? Can you determine the tag? Yes, right? We can determine the tag. So if someone says that, okay, how to solve this, then you can directly solve. Otherwise, let's suppose you forget, right? Then you assume block size to be X. Is this a good idea to assume block size to be X? Or some 2 power something? 2 power, is it a good idea, or the X is X is a good idea? 2 power is a good idea because ultimately we know that you can make it 2 power X, doesn't matter. Ultimately, no, it is in 2 power. So let's just keep it 2 power because it will make our calculation little easier, right? Okay. So you know that this is X because block offset is X. Then how many number of lines? 2 power 10 minus X. So this is 10 minus X. Ultimately, this is 10. See, ultimately, this is a cache size, isn't it? Tell me, isn't this this is 10? Ultimately, this has to be 10. But anyway, if for the sake of writing, I'm writing. If whole is 16, then can you tell me what is this? This will be 6. So that's how also you can find out your answer. This is your tag, right? This is your tag. That's how also you can find out your answer. It is not an issue. All I'm saying is that if you have given cache size and memory size, then it is a direct multiple. Okay, tag bits will tell you that how much multiple is main memory of your cache memory. Okay, because you understood, right? I mean, you don't need to by heart it. You should also understand that what I'm trying to say. If these are the 5 bits, it means there are 2 power 5 variations that you can have here, which means 2 power 5 blocks can map to this particular line, isn't it? Okay. So let's solve more questions. You will get to understand more. Let's see this GATE 2017 question. Consider a machine which is byte addressable. They are saying that uh, that man memory size is 2 power 32 divided into blocks of size. Block size is given. Okay, assume that. Okay, cache size, cache lines. They are saying that 512 cache lines. So can you tell me cache size 2 power 9, these many lines, and 2 power 5, right? 2 power 14, basically 2 power 14. Okay, these many bytes. Now they are asking tag. Can you tell me tag directly? 32 minus 14, right? It is 18. I mean, they have given the block size also. So I think if you do using another method, then also it is okay. This is 32. And then this is 32 bytes. It means it is 5, right? It is 5. And number of lines is 9. Okay. This is 14. Then remaining is 30. Okay. That's also you can, remaining is 18. That is also, that is how also you can solve, not an issue. I will say for this question, you can solve like this. Okay. For this question, you can solve like this. Let's see this question. What they are saying. This is byte addressable. Then 32 bits. Okay. Man memory size is given to be 32 bits, 2 power 32. Assume that direct map. Cache of size. Okay. Cache size is directly given to you. It is 2 power 5 into 2 power 10, right? Which is 2 power 15, right? Can you tell me tag bits directly? Do you even have to read this? Do you even have to read this? No, right? You can directly tell the tag bits are 32 minus 15, which is 17, isn't it? That question has been asked very recently in GATE 2021. Okay. So see, they have done something. Okay, K is associated, I don't know. But yeah, you can directly find out, right? Have you understood this method? Let me know. The tag is very powerful. It is telling you that how much multiple your main memory is of your cache size, right? Okay, cool. Now let's just do more questions and let's see if you are able to answer. Let me just ask you one more question here. Let's suppose that I say main memory size is, let's suppose, 34, 2 power 34, which means 34 bits. Okay, it is having 34 bits, let's suppose. And I also give you that number of lines. Okay, let's suppose these are, I have 2 power 5 lines, right? Okay, from this information, can you tell me, is this possible to tell me, let's suppose, tag, or it is possible to tell me index? Which of this is possible? Okay, or maybe byte offset or cache size? Which of this is possible from this particular information? See, let me write the question also so that you can refer later on. So which of this is possible to find out? So see here, this is total is 34, which is given to you. In between something is given that, okay, this is 5, right? Now the remaining is how much? Remaining is 29, right? So if this is, let's suppose, k, then this will be 29 minus k, right? So you don't know that you don't know that exactly how much is tag, exactly how much is offset, but you know the index, right? You know the index, but and also you don't know the cache size. Okay, now let me just modify this question. Now suppose they say they say tag is, let's suppose they say tag is 17 bits, then what is the cache size? Can you calculate the cache size now? If tag is 17 bits, in bytes. How many bytes? See, do you have to do so much of calculation? This is 34. This is given to 17, right? It means remaining is 17 only, right? Remaining is 17. So this is the cache size, right? This is a cache size. So what is the answer here? 2 power 17 bytes. Okay. Now, with the same question, let me just ask you. Suppose they ask you, size of line. Then, can you tell me? See here they have given you some information, right? Let's just check that information. They have given you, this is total 34. This is 17. Cache size is 17, right? This is cache size. And also number of lines are, they have given is 5. Then they have also given this is 12, right? This is 12. This is 17. They ask you the size of a line in bytes. So how you can calculate the size of the line? Using this 12, right? Using this 12. So what is the size of line? It is just 2 power 12. Using this 12, you can say the size of the line is 2 power 12 bytes. Okay. What could be the other way? The cache size you can find out. Cache size is, you know, that this is 34, this is 17. So 2 power 17 bytes is your cache size, right? And if this cache is having, these many lines, then what should be the number of lines? I mean, the line size, you can basically divide by 2 power 5, then you can get 2 power 12 bytes. Okay. This could be other way, but that's fine. If you have not understood this, then that is okay. They are asking basically line size. It means they are asking this particular field, right? Okay. Understood? Okay. So I hope you understood that what this tag mean. Okay. I just want to convey that what this tag mean. Let's just solve this question. This question is saying consider direct mapped cache with 256. Okay. Here this is lines, 256 lines and 16 bytes block. Okay. So the block size is given to you and a number of lines are also given to you. So which means they are saying this is 4. 256 means 2 power 8, right? This is number of lines are 8. I mean 2 power 8. In this address, this particular 0x12, which in the hexadecimal, maps to the same line h which of the following address. So this is, what is the line number of this? What is the line number? You assume that memory is of 1, 2, 3, 4, 5 of 20 bits, okay? So if it is 8, this is 4, then what is the, how many bits are for tag? How many bits are for tag? 8 bits, right? Okay. Now, you just ignore this because this is 8 bits, initial 8 bits. In the hexadecimal, this one means 0001 in binary. Basically, this means 0010. Each of this you have to write using the 4 bits, right? This the initial 8 bits are this. So this is 34 in the hexadecimal. Now, can you tell me which one is matching? A C, and D, right? A, C, and D. Okay. Is this understood to everyone? Let me know if there is any doubt. That see, I'm saying the line number here is 3, 4 in the hexadecimal. It's not decimal, it's hexadecimal. Then which of these is having 3, 4 in the hexadecimal? This one, and this one. Okay. Given that, okay, I've also given that, okay, 20 bits are the total memory size. Let me know if that is okay. See, let me just explain you that what is this 1 2 3 4 5 means. What is this 1 2 3 4 5? It is basically in the hexadecimal, right? Which means the address that I'm saying here, address is 0x12345, right? 0x, then 12345. It means in binary, the address will look like, in binary, you convert this 1 into 4 bits if it is hexadecimal. You convert this also into the 4 bits. You convert this 3 also. You convert the 4 also. You convert 5 also, right? So this is in the binary. But instead of writing that much and then you will get confused, they've written in the short form, which is the hexadecimal. Okay. Now these 8 bits are your line number, right? They're asking which of the following having the same line number. You remove the initial 8 bits and take these 8 bits then, right? This, and this. So ACD is the correct answer. Okay. As you can see here, ACD is the correct answer. Okay. Now let's see this question, which I have taken from IIT Delhi. So what they are saying, below is the sequence of four binary memory addresses. Okay, this is memory address. These are the addresses, right? Now, can you divide this into index tag? So they are saying that with 16-bit in order, they are used with the reference memory. Assume that cache is initially empty. For each reference, write down, okay, these are 16-bit address, right? Write down the tag index and indicate whether that reference is hit or miss. Okay, so I think like there should be some more information, right? That what is the size of cache or something. Okay, just a second. Let me just check it. Okay, so this is the question, but I think there is some more information that is given here. Let me also write that information, right? Okay, so suppose that this whole information is given to you, and now you just find out the answer of this question. So what they are saying, let's just see. So they are saying that memory is byte addressable and there are 16 bits. Cache has 8 rows, right? So there are 8 rows that are in the cache. Okay. So which means there are 8 lines. So can you tell me number of index bits, which will be 3 bits, right? It is written here. Okay. And the offset is 4. So basically you have 9, 3, and 4. Your division is 9, 3, and 4. Okay. So suppose your division is 9, 3, and 4. 9, 3, and 4, which means this is offset, this is your tag, and this is your index, this is your tag. Now they are saying that given this address, can you first of all tell me what are the index bits? See, this is the index. You just forget about these 4. Then this is the index. So can you quickly tell me what is the index? 011, right? Here 111, here 011 again, here 010. Is this okay to everyone? Okay, tag also you can definitely write, right? So initial 9 bits you can just copy here. These 9 bits you can copy here. This is the tag. Okay, anyway. Now you tell me, whenever you are referring this at a first time, will it be hit or miss? Assume that cache is initially empty. Okay, so it will be obviously miss because there is nothing in the cache, right? So that's why it will be miss. So what I should write here? This is miss. Now cache has, I mean, the cache line number 3 has something, right? Okay. Now you are again accessing this address. This address will tell you hit or miss. Tell me. See, the line number 3 has got something, but this is line number 7. Line number 7, you are looking at the line number 7. Line number 7 has not got anything, right? Line number 7 has not got anything. So that's why it is also miss. So now line number 3 and somewhere line number 7 has some data, right? And how to know that data? What is the data? Using the tag we know, right? Using the tag we know. So line number 3 has got some data. Line number 7 has got some data. Now you are again interested in line number 3. Tell me, is this the data already available? You need to check with the tag. See, this is the tag currently, right? This is the tag currently associated with the line number 3. It is having this particular data. Is this same as this? Just check. Since it is same, that's why it will be hit. Understood? Why it is hit? Because currently line number 3 and 7 is filled, and line number 3 is having data that can be told by this particular tag, that it is having data of this block, right? You're also interested in the same tag. That's why it will be hit. Now line number 2, this is line number 2. This is hit or miss. Line number 2 anyway doesn't have anything, so that's why this is miss. Understood? So miss, hit, and miss. Nice question, isn't it? Let me know if you have understood. See, what I'm saying here is that this particular address you access first, which means you filled something in the line number 3, and what you filled actually is basically this is the block number. If you even ask me the block number, then what is the block offset? 4. Okay, you just forget about this 4. Then this block number is basically currently in line number 3. You can convert that to the decimal, doesn't matter. So you can convert that to the decimal. This block number is currently in the line number 3. But you can also say that, see, this is the block number. That is fine. These are the block numbers. Now you can say that, okay, you are filling the line number 3 with some block. Now you can also say with the tag that you are saying that, okay, this is the tag, right? This is a tag. So it is having currently this tag. Now you are filling somewhere. I mean, you are going to the line number 7. Obviously, this is empty because line number 3 you just filled. Line number 7 you can fill here. Now you are again going to the line number 3. Does this also contain the same data that you are looking for? Then you will check that, okay, currently line number 3 is having this much tag, right? This is the tag, and you are also interested in the same tag. So that's why it is a hit. Then line number 2 anyway doesn't have anything. That's why it is a miss. Okay. Now let me just add one more line here and tell me whether it is hit or it is miss. Okay. Let's just add one more line here. So you can fill out these things later on. Okay. But let's suppose that this is a hit or miss. See, what is the index here? Index is you forget about these 4, then this 0, 1, 1 is index. So you are looking at line number 3. Line number 3 already has something. But is this the same thing that you are looking for? You are looking for this much, right? This tag. But line number 3 currently has this tag. This tag, right? So that's why it is a miss. Okay. It will be, sorry, let me just remove this. It will be miss. Okay. Now you tell me one more thing. Suppose if I just modify this. Okay. This is in the sequence. In the sequence I'm modifying, right? In the sequence I'm modifying. Let's suppose I say this. Okay. In the sequence I'm doing all the thing. Then can you tell me it is a hit, miss? What is this? So see, I'm interested in this much. What is the index? You forget about these 3 bits are index, right? 1, 1, 1. So you are going to the line number 7. Do line number 7 also contain the data that you are looking for? So basically you are looking for, you are looking for this tag, and it also has the same tag, right? So that's why it will be hit. Okay, this will be the hit. Understood? Okay. Now let's just see this particular question, which I have taken from this university. Okay. So what they're saying, that let's suppose you just have 3 bits of address. Okay, not 3 bit. This is 38. Okay, there are multiple bits. So they're saying, assume we have 4-line direct mapped cache, which means there are only 4 lines. Which means for the index bit, how many bit you need for the index? Is there only 4 lines? Then you need just 2 bits, right? Okay. So in middle, you just need 2 bits here. So you will say it is just 2 bits. Okay, maybe 3 they have they might have written in the decimal or the hexadecimal, but doesn't matter. Okay, this is basically you can write it 1 1. Okay, in the binary. And then what they're saying is, okay, no other information is given. So they are saying, if this is the address in which you are accessing, then initially tell me what it will happen. Initially you are going for the line number 0. You are interested in line number 0. It will hit or miss. Initially the cache is initially empty. Okay, initially obviously it will be miss, right? It will be miss. Now again you are going to the line number 0. Now you tell me it will be hit. Why? Because you have just put for the tag 0, right? The tag 0, currently it is having the tag 0. That's why it is hit. Now you tell me. Now again you are going to the line number 0, but this time you are looking for some other tag, right? Which is 1. So that's why it is miss. Now you are going to line number 3. This is the very first time you are going to the line number 3. Can you tell me it is hit or miss? This will be miss, right? You have not put any data here. Now you tell me this is the again you are going, yeah, that's interesting. Now you tell me this is hit or miss. See, you are going to the line number 0, but the currently it has the tag 1, right? Currently it has tag 1 because the latest you have updated the data. So that's why it will be again miss. Now this will be hit or miss. This is hit, right? So miss, hit, miss, 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 hit. Miss, hit, miss, 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 hit. Okay. Yeah, that's correct answer. Okay, you also tell me this one. Let's suppose if I just ask you 1 3 7 0 3 6. Tell me for these two also in the same sequence. So 3 you have updated, that's why it is miss. Now again, see, 3 you have updated with a different tag. Now 3 you have updated with again different tag. So that's why it is again miss, right? So both are miss. Okay, understood? Okay. No, offset is not of any use, and it should not be actually, right? Offset doesn't have any role to play in hit or miss, and it should not. Why it should not? Because offset is once you hit it, okay, once you are final, okay, that the data is here. Now how much inside to go in the block? That's where this offset is important, right? Otherwise this offset is not important to you, right? Offset doesn't have any role to play whether it is a hit or miss. You are playing with the block number and the line numbers, where the offset doesn't have anything to play. See, your hit and miss are determined by this is the block number, this is a line number, right? This is a line number. So hit and miss you are determining with this block number and line number. Offset doesn't have anything to play here. Okay. Okay. Now let's just see some more questions that we have here. Let's see this question. This is also one of the very tricky question. Let's just see what they're saying. They're saying a system has 1 GB of byte addressable memory. So 1 GB means 2 power 30. This is the memory size. Cache size is given to you 2 power 8 into 2 power 10, which is 2 power 18 bytes. Identify two distinct memory that map to the same location in cache. Okay. So they are saying that if you have 30 bits, right? 30 bits. Now, with these 30 bits, you need to tell me any two memory locations that are mapping to the same cache line. Okay, to the same location in cache, which means the line number should be same. The line number should be same here, right? So how much is the line number? 1 byte per block. Block size is given to you 1 byte. Okay, block size is given to you 1 byte. So can you tell me number of lines or number of blocks? 2 power 18 lines only, right? Because this is the cache size upon block size will tell you the number of lines, right? So this is 18. So 18 is the index bits, right? This is 18. Now, how much is your this much? This block size is given just 1 byte. Okay. So what is the block offset? This is interesting. What is the block offset? 0 bits, right? You don't have any block offset. I mean, the line number and the block number are actually same. Okay. Line number and block number are actually same. You don't have the block offset here. That's fine. Is this okay to everyone? Because this is 1 byte, which means there is no block offset. I mean, the line number, whatever the line number, sorry, whatever the block number, not the line number. So every block just have 1 byte. Okay, every block just have 1 byte. Okay, which means I don't need to go inside it. Okay, I just say that okay, whatever the block number is same as my byte number, which means byte address or block address are like this. See, let's suppose this is 1 byte I store here, another byte I store here, 1 byte I store here, 1 byte I store here, right? Let's suppose if a block is containing 4 bytes, then the block number and the within the byte will be different, right? If the block is just containing 1 byte, okay, then if I tell you the block number or the block address, okay, sometimes we call it block number, some people call it block address. Both are fine, right? Block address or the block number. So if I tell you the block number, isn't it same as the byte number? Or both are different? Tell me. This is, I am saying this is the block number, let's suppose 0, 1, 2, 3. This is the block number 3. Isn't it the byte number 3 also? Right? So here the block number is same as byte number. If you don't prefer to call it number, you can call it address also. Block address is same as byte address. Okay, if I'm saying that okay, this is 0th byte, one, I mean 0th block, first block, second, third, and whatever the block, right? Let's suppose I say that this is the block number is, let's suppose I say 200. Isn't it the same as byte number? So block number and byte number same. So that's why there is no offset here. Okay, that's fine. I mean, there is no offset, that's fine. So these are the 18 bits that you have. Now, if they're saying that tell me any two addresses which are mapping to the same line, can you tell me? Maybe, right? You can write some random number here, maybe 0100. I mean, any 18 bits. You say that okay, maybe you can say something like this. That if this is the line number, you can definitely say that you can write any 18 bits. Maybe I can write something like this: 001010. Right? These are the 18 bits, and now remaining are how much? This is 30. Remaining are 12, right? So these are the remaining 12 bits. You can write any 12 bits here. Okay, let me write 12 bits. Okay, these are the 12 bits. Now this is mapping to some line. Can you tell me another address which map to the same line? Isn't this address also mapped to the same line? Isn't this address also mapped to the same line? Tell me. I mean, all you have to do, these should be same, right? These should be same. Isn't this address also have to also map to the same line? Both are having same line, right? Both 30-bit address has same line number, isn't it? Okay. Now, let's just make it more interesting. Suppose, suppose if I say that there is some address X, okay, which is having some line number, right? There is some address X. Okay, let's suppose this translation is X. Okay, the decimal is X. Now, can you tell me after how much? After how much? I mean, what should be the next address which is sharing the same line number? What is the next address which is sharing the same line number? See, what is the immediate address? You add one here. This is the immediate address, isn't it? This is the immediate address, which means it will be 0, it will be 1, and everything will be same. You can add one here. It is the immediate byte address. Okay. So that is the immediate byte address. So understood? The immediate address is you just add one here, that will be the immediate address. Okay. Add one here, that will be the immediate byte address. You add two here, 2 byte. I mean, after this, if you add two here, these will be two more bytes, then two more bytes. Then can you tell me what should be the next byte address that is sharing the same line? You should be adding one here, right? One here, isn't it? You should be adding one here. See, if you add anything here, won't it change the line number? If you add one here or something. So what you should be adding such that the line number is same? You should be adding one, okay, all the zeros, all 18 zeros, isn't it? You should be adding 18 zeros. Okay. This is the least number you can add such that the line number is same. Okay. So this is the next address, minimum address I can say. Okay. 0010. You add one here and everything here is same basically. So this is the least address or the next address which share the same line number, isn't it? Are you getting my point? See, you want to keep these same, right? You want to keep these same. So what you should be adding? The only very simple thing I'm asking. So if X is some address, then after X plus 2 power 18, this is 2 power 18 basically, you will share the same line number. So X plus 2 power 18 share the same line number. Okay. The next address does share the same line number. What is the next address? X plus 2 power 18 plus 2 power 18, right? I mean, you can think like it is a new question. Okay. From this, you add one more one here, right? This is sharing the same line number. So if X is having some line number, then X plus 2 power 18 is sharing the same line number. Okay. Anyway, I'm just doing it too much, I think. But have you understood? Okay. So they're just asking any two address. We have given some address, right? That is fine. Okay. So here we are saying that that based on the placement itself, we are dividing it into multiple parts. Which means if I am saying that this can be just going to only one of them, then this is direct mapped. If that can go to two of them, then this is set associative, right? This is set associative. So that's what we are saying. I mean, that's how we are dividing. So now let's just see the second part here, which is the second way of classifying the cache memory. It is a set associative, right? The direct map is over in the sense that we have seen how it is working, and we have seen many of the questions. Now let's see the set associative. So direct map says a block within the given address can only be mapped to single location of the cache. Okay. Set associative says that a block can be placed anywhere within the set of locations. A block can be placed anywhere within the set. Okay, that's what set associative says. So let's just start this set associative. Should we start today or tomorrow? Tell me. Okay. So let's just see how much it is. Okay. So what we can do, we can start it tomorrow. Okay. We can start it tomorrow. So we will be starting with set associative tomorrow. So today we have just seen more questions of the direct map. Now, are you comfortable with the direct map? That what direct map is doing? So basically, I'm saying that if this is the cache, then this is the memory, then you are just mapping the lines here or the blocks here to this particular location or the line. So this is just in the cyclic fashion, which means if this is mapping to the line number 0, line number 1, line number 2, line number 3, and let's suppose there are only 4 lines, then can you tell me directly this is mapping to whom? To the line number 0, right? Again repeating 1, 2, 3. Okay, cool. So that is all. We will start the set associated tomorrow. Yeah. Thank you so much. Okay. Thank you, everyone. Take care. Bye bye.